Okay, so in chapter 2, we talked about ionic compounds and then naming, and in chapter 3, we talked about balancing chemical reactions and then using stoichiometry to keep track of mass in chemical reactions. Now in chapter 4, we're going to dive specifically into reactions that occur in water, known as aqueous solution. That's the term for solutions that are in water. Now, we talked about solutions a little bit in chapter 1. So remember, a solution is simply a homogeneous mixture, something like this case where we've got copper sulfate dissolved in water. And we need to expand our vocabulary a little bit. We need to add some more terms to our knowledge. And with solutions, two very common terms are the solvent and the solute. Solvent is the component of the mixture that exists in the greater amount. Most of the time, we think of this as being the liquid component of a solution. Now, not all solutions have to be in the liquid form, but the vast majority of them are. Those are the ones we're most familiar with. And so we think of the solvent as being the liquid component. Now, you could have a mixture of two different liquids, in which case the solvent there would be just the liquid that exists in the greater amount. The solute is whatever is dissolved in the solvent. So most of the time it's a solid, as in this case with copper sulfate powder, or it could be table sugar or table salt or any other number of solid compounds that dissolve in water. An additional term that we use specifically to describe aqueous solutions is the term electrolyte or non-electrolyte. And you may have run into those terms before, particularly in Gatorade commercials or sports drink commercials. And you might have this sense of electrolytes as being these things that boost your muscles and some kind of power for bodybuilding. But in reality, that's not really what electrolytes are. Electrolytes are simply materials that conduct electricity in aqueous solution, in water. So what exactly does that look like? Well, let's take this case here where we have a light bulb that's connected to a circuit, and over on the side there's a battery somewhere powering the circuit. But there's a break in the circuit where the two electrodes are dipped into water, but there's nothing other than the solution connecting the two electrodes. Now, pure water itself actually does not conduct electricity. This may seem counterintuitive to you if you think about hair dryers in the bathtub, etc. But in pure water itself, it does not have any ions in it, so it does not conduct electricity. Now, the water in your bathtub does have ions and dissolved salts in it that do conduct electricity, and so it is still unsafe to put a hair dryer in the bathtub or the toilet. But pure water itself does not have any ions, and so does not conduct electricity. Now, molecular compounds like sucrose, which is table sugar, and has no ions involved, and so that would not break up into ions in solution, and so that would be termed a non-electrolyte. That also does not conduct electricity. However, if we add sodium chloride to a water solution, now we will have ions. We've got an ionic compound. The sodium chloride will break up into its individual ions, and those ions then conduct electricity. And so sodium chloride is termed an electrolyte when it's dissolved in water. So just to give a short definition then, an electrolyte is a compound that dissociates into ions in water. And as we'll see, most ionic compounds are electrolytes. We'll see some examples later where ionic compounds are non-electrolytes, but the vast majority of ionic compounds are electrolytes. A little bit more detail on this. How exactly do electrolytes break up or dissociate into ions in solution? Well, let's think about this by looking first at water itself. Water has oxygen shown in red there, and then two hydrogens attached to it. And the oxygen and the hydrogens don't share their electrons equally. We'll talk in much more detail about this in chapter 8 and chapter 9. But for the moment right now, just imagine that oxygen hoards more of the electrons. And so around oxygen, there is a partial negative charge since it holds a little bit more of the electrons than the hydrogens do. And the hydrogens, because they have a little bit less than their normal share, end up having a partial positive charge. So essentially, water just has two sides to it. It has a slightly negative side and a slightly positive side. Now, when we dissolve an ionic compound in water, water will align the partial charges of its molecule around each ion in order to satisfy that ion as much as possible. Let's just take the example here of sodium chloride. If we have a solid sodium chloride, it's got its three-dimensional lattice with sodium and chloride in green. Sodium is in purple and chloride in green. And then as that dissolves into solution, water comes and surrounds each ion, the chloride ion and the sodium ion, in such a way as to satisfy their charges. So here, if we look at the chloride ion, you'll notice that all of the partial positive ends of water are aligned towards the negatively charged chloride. And so we have negative with positive, and that stabilizes the negative charge. Likewise, the sodium, which is a positively charged ion, all of the negative sides of water are aligned around that to satisfy that charge. And that's essentially how water acts to dissolve ions in solution and how ionic compounds break up. We can write an equation for this dissolution process where we simply start with the ionic compound as a solid plus water as a liquid, and then we go to the individual ions as in the aqueous state, where, remember, aqueous means that it's dissolved in water. We don't have to write water anymore because it's implied by the aqueous state. The compounds now no longer exist as the discrete molecular formula. We would no longer refer to it as being sodium chloride, but we refer to it as individual solvated ions, sodium ion and chloride ion solvated. Now, molecular compounds such as methanol, so non-ionic compounds, can also dissolve, and water does arrange itself around those molecules as well, but we don't get, these compounds do not break up into ions. And so remember, ionic compounds are metal with non-metal. Molecular compounds are just non-metals together. Those compounds, with the exception of strong acids, strong and weak, which we'll talk about in a moment, those compounds do not break up into ions at all. Okay, so we know a little bit more how electrolytes break up into solution, but there's also a distinction of strong versus weak electrolytes. And then there's even non-electrolytes. How do we distinguish these? Well, strong electrolytes are those compounds which fully or mostly dissociate in solution. A couple of classic examples of this: sodium chloride, that one fully dissolves, dissociates in solution, or HCl. This is a molecular compound, but it is a strong acid where hydrogen acts as the cation, so you get H+, and chloride is then our anion. There are a few examples of strong acids. We will talk about those in a couple lectures, so hold on for that part. But we'll go through some details later on of exactly what acids are and what the list of strong acids is. Regardless, soluble ionic compounds and strong acids fully dissociate in water, and so those are strong electrolytes. Weak electrolytes, on the other hand, are compounds that only partially dissociate in solution. So these are going to be primarily just weak acids, molecules that are molecular compounds, not ionic, that have hydrogen acting as the cation, but only to a small degree, rather than breaking entirely up into hydrogen cation and then whatever the anion is. They only do it to a partial degree. And a common example of a weak acid is acetic acid, which is shown here, CH3COOH, where the H is my acid. It will dissociate to give H+, and then the acetate anion. But it only does so to a very small degree, maybe about 10% in solution in water. And so this is then a weak electrolyte because there's less ions, and so less ability to conduct electricity. This is illustrated by this example here, where all the way on the left we have glucose, which is a fully molecular compound. It's not a weak acid or anything. This is a non-electrolyte. Nothing dissociates when you dissolve it in solution, and so there's no electricity conducted. In the middle is our example with acetic acid, just shown here. So it's a weak electrolyte. It does conduct electricity, but the intensity of that electricity is weaker compared to the strong electrolyte, HCl, all the way here on the right, then conducts a lot of electricity, and so you see a very bright light bulb. The last thing here to note is just that all water-soluble ionic compounds are strong electrolytes. Strong acids, which are molecular compounds, strong acids, and all soluble ionic compounds are strong electrolytes. In the next couple lectures, we'll go through why we specify water-soluble ionic compounds, and we'll see some cases of ionic compounds that would not be classified as electrolytes.